Good morning, everybody. Let's get ready for some physics. I like your picture, Kenny. We give people about 1 minute to join and then we'll start. And just so there's no panicking, I found my hat. We can lecture like normal. Yay, hats. I'm almost embarrassed to tell you how stressed out not being able to find that hat was for me. I literally tore my house upside down and it was hanging on the back. Okay, I do have the recap on, so let's just do a quick little recap of torque. And that's pretty much all I'm going to cover today is torque. I'm going to skip angular momentum, so after today, we are officially done chapter 12. So, let me hold this for a second. Let's manage participants. Mute all, yes. Okay. So torque is the rotational analog of force. Just like forces cause linear acceleration, torques will cause an angular acceleration. And the way we define torque, what's going on here? It's deleting everything I draw. Whoa. Okay, what happened with that? Okay, so the way we define torque is it is the magnitude of R times the magnitude of F times the sine of the angle between the two. R is the distance from the axis of rotation to where the force is applied. F is the magnitude of the force, and theta is the angle between the R vector, which goes from the axis of rotation to where the force is applied, and the F vector. And by convention, we consider torques that would tend to produce a counterclockwise rotation as positive, torques that tend to produce a clockwise rotation as negative. And Newton's second law for rotations basically says the sum of the torques on an object equals I, which is the moment of inertia of the object. It's the rotational analog of mass times the angular acceleration. And again, keep in mind that when we are looking at the angle, we always draw the two vectors tail to tail. So for example, for this particular one, if I have my axis of rotation right here, and I've got some sort of rod or something. Let me just get rid of that, that's confusing. And I want to know, let's say for F1, what is the angle I would use for the torque? Well, R1 always points from the axis of rotation to where the force is applied. So my R1 vector for this particular case points to the right. Now the angle is not 30 degrees when calculating the torque, because I would draw the two vectors tail to tail. So here's my R vector, and then here's my F1. So if this angle right here was 30 degrees, then the angle between R and F would actually be 120 degrees. So whenever you're going to calculate the torque, the angle that you use is the angle between the R vector, which points from the axis of rotation to where the force is applied, and the force vector. And again, torques can be positive or negative, just like forces can be positive or negative. By convention, we call a force to the right positive, a force to the left negative, but we can always change that up. So for this particular case, if I have two forces, F1 and F2, these torques are not producing rotations in the same direction, so they can't have the same sign. So in this case, F1 would cause this thing to rotate counterclockwise. So we consider F1 to produce a positive torque. F2 would cause this to rotate clockwise. So that would be a negative torque. So that's just sort of what we covered so far. And before we jump into a problem, I want to ask you a clicker question along those lines. So this is clicker question 12.-5. It says 3 forces labeled A, B, and C are applied to a rod which pivots on an axis through its center. And the cosine of 45, sine of 45, square root of 2/2. Question is, which force causes the largest magnitude torque? So force A is a distance L away. Force B is a distance L/2 away. And force C has twice the force, but it's only a distance of L/4 away. And let's try and do this as a pole. See how this works. Okay, so I've got a pole launched. If you're on a computer screen, hopefully you should see the pole pop up. I'm not sure if you can see it when it's on a phone or iPad if you're watching from there. But if you can, take 30 seconds. I've got 3 different forces. Each force is exerting a torque. The question is, which of those 3 forces produces the largest magnitude torque? We're not worried about whether it's positive or negative, just which one produces the largest magnitude torque. We give people about 30 seconds. Right now, we've got A is the majority. 55%, 58%, 64%, 65%. It's a 73%. Oh my God, it's a runaway. 73%. All right. Gonna give another 10 seconds for people to vote. Let's end it. And 5, 4, 3, 2, 1. Share the results. Okay, we have 70% of those responding saying A causes the largest torque. Let's go through it. So again, for each of these, can I show this both at the same time? Okay, so torque, again, in general, is just going to be RF times the sine of the angle between them. So let's look at each one. For force A is located a distance of L away, and the magnitude is F. So my torque is going to be L times F times the sine, in this case, of 45 degrees, which is square root of 2/2 times LF. Force B is located a distance of L/2 away from the axis of rotation, so that's my R. It still has a magnitude of F, but now the angle between the force and the R vector is 90 degrees. So I get sine of 90 degrees. So what I get is LF/2. And then for case C, now C, the force is located a distance of L/4 away, but it has a magnitude of 2F. So what I have is L/4 times 2F. And again, the angle in this case would be 90 degrees. What I get is LF/2. So B and C both produce the exact same magnitude torque, but A has a larger magnitude torque than either one. So the correct answer was A.
It's easy.
Woo! Okay, let's go back to this. I was looking at an example problem kind of as we ended class on yesterday. So I'm going to do it again, but it was problem 1220. Said a 20 center diameter disc in the figure can rotate on an axis through its center. What is the net torque about the axle? And what I was talking about first was, let's think about the signs of the torque. Any torque that's going to tend to produce a counterclockwise rotation is considered positive. Any torque that would tend to produce a clockwise rotation is considered negative. So I just labeled these because they weren't labeled 1, 2, 3, and 4. So in case 1, force 1 would cause this to rotate clockwise. So it is a negative torque. Forces 2 and 3 would both cause this thing to rotate counterclockwise. So they are positive torques. And force 4 is not going to tend to produce any rotation. And the reason is you could kind of see that if I'm actually exerting a force in this direction, there's going to be no tendency to cause this thing to rotate. But in terms of the equation RF sine theta, the angle between force 4 and R4 is going to be 0 degrees. Okay, so let's actually go and calculate this whole answer. So one, what I did, just to be clear, is labeled the angle that we would use when calculating each torque. And again, keep in mind that when you're looking at the angle, you're always drawing the vectors tail to tail. So let's just look at 2 of these. So for force 2, so the R vector would always point from the axis to where the force is applied. So for force 2, my R2 vector would point to the right. My F is always pointing in the direction it's pointing. So here's my F2. So if this angle here is 45 degrees, that means this angle is 135 degrees. That's the angle between force 2 and R2. So that's the angle we would use. So if I want the sum of the torques, keep in mind torque 1 is producing a negative torque. Torque 2 and 3 are both producing positive torques. But let's just write the entire thing out. What this would be let's subtract this. R1, so negative R1, F1 sine of theta 1. And again, it's negative because it's tending to produce a clockwise rotation, plus R2, F2 sine of theta 2, plus R3, F3 sine of theta 3. And let's just say that we didn't know whether force 4 was going to cause a positive or negative torque. So just write this as plus R4, F4 sine 4, sine theta 4. Now in reality, this is not going to produce any torque at all because the angle between the force and R is 0 degrees. So for each one of these, do we have the values? We've got 5 centimeters, and F1 is at a distance of 10 centimeters away. So what we have is negative 0.1 meters times F1, which is 30 newtons, times the sine of 90 degrees, plus R2, which is 5 centimeters, so 0.05 meters, times 30 newtons again, times the sine of 135 degrees, plus R3, which is also 5 centimeters, 0.05 meters, times F3, which is 20 newtons, times the sine of 90 degrees, and then plus, so here, what would be the R that I would use? This is a distance of the radius away. It's a 20 centimeter diameter disc, which means that the radius is 10 centimeters. So this would be 0.1 meters times 20 newtons. But the angle we would use would be 0 degrees. So this whole torque from force 4 is 0. So once I just multiply all of these out, what I'm going to get is the sum of the torques is equal to negative 0.94 Newton meters. So that is the answer to 12-20. Expect a fairly straightforward question like this on the upcoming quiz, just in terms of calculating the torques. Expect to have some kind of object where you have 2 or 3 forces acting on it. You need to figure out the total torque by looking at the torque of each one added together. If it tends to produce a counterclockwise rotation, that torque is positive. If it tends to produce a clockwise rotation, that torque is negative. And also keep in mind the units of torque is the Newton meter. It is equivalent to a joule, but we never ever use the unit of joule for torque. Joule is sort of reserved for work and all forms of energy. So let me just pause this for a second, open it up to any questions on this particular example problem, knowing that you're probably, oh, this is not a recap anymore. Bump, 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 bump. Knowing that you're going to see something like this again. Any questions I can answer on how to calculate the net torque in this particular problem?
Given that the units of angular momentum and energy are the same, can you—
Not angular momentum, the units of torque and
units
energy.
of torque, yes.
Yes.
Can you use just, like, if you have a certain amount of energy that is all converted into torque, would you not need any additional information?
No, great question. So this is one of the things that's confusing. Just because the units work out to be the same, there is no direct correlation between torque and, you know, potential energy or something like that. I can use conservation of energy with objects that are rotating and look at the rotational kinetic energy 1/2 I omega squared, but I would caution people strongly not to try and relate energy to torque just because the units work out the same.
Okay, thanks.
Yep. Okay, I have, before I move on, I have a question for you. I want to pose as a, can I do a clicker question while I'm in a poll? Yes. So here is a question for you. So this will be a yes, no. So it's a two-part. A, yeah. I forgot I can't do that here. Erase. You know what? Let me stop this for a second. Now that I've gotten used to OneNote, I'm not a big fan of the other one, OneNote. Oh, okay, so let me just open up a new. All right, so here's the question. Two-parter. If that's a question. If the sum of the forces acting on an object is 0, does that mean the sum of the torques on the object is also 0? And second part of this is if the sum of the torques on an object is equal to 0, does that mean the sum of the forces on the object is 0? So let's say this is yes, no, yes, no. And so kind of asking this as a clicker question, A, B, C, D. We've got yes, 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 no, 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 yes. So two-part question. Part A is sort of, or part one, if the sum of the torques, or if the sum of the forces on an object is 0, does that mean the sum of the torques on the object is going to be 0? Yes or no? If the sum of the torques on an object is 0, does that mean the sum of the forces on the object is 0? Yes, no. Let's open up a poll, relaunch polling. Okay, so as a clicker question, what do you think? If I know the sum of the forces in an object is 0, does that mean the sum of the torques is also 0? If I know the sum of the torques is 0, does that mean the sum of the forces is also 0? What do you think? Yes or no in each case? We've got a big majority say B so far, 65%. And followed by C. So let me give you guys a hint. The correct answer is not B. And I'm not sure if you can change your answers on a poll or not. Can you change, anybody change an answer? Can you change your answer on a poll?
I don't think so.
No? Okay. So let me just end this and kind of go through it. So the results were About 67% of you said B, yes and no. Let me just show you quickly. The answer is, let's do this in blue, draw. Well, let me first give you an example. If the sum of the forces on an object is 0, does that mean the sum of the torques on the object is 0? Well, here's a simple case. Let's say I have a rod that's pivoted in the middle, and I exert the exact same force, but in opposite directions. So I'm exerting a force to the right that's acting straight up, a force on the left that's acting straight down. In this case, if these forces are equal and opposite, the sum of the forces is equal to 0, but the sum of the torques is not equal to 0, right? Each one of these forces is tending to produce a counterclockwise rotation. So both of these forces produce a positive torque. So here's a case where the sum of the forces is 0, sum of the torques is not. Now, what happens for B, or part 2? Is it possible for the sum of the torques to be 0, but the sum of the force is not? And the answer is that can also happen. So 2 classic examples. Let's just say I have an object which is pivoted about the middle, and I exert a force right on the axis of rotation. Here, since it's acting right at the axis of rotation, the R value that I would use would be 0. That particular force is not going to cause any rotation. Or another example would be, let's say I've got, again, this is pivot at the middle, but I'm exerting forces that are both acting in the exact same direction. So here, this first force would tend to produce a counterclockwise rotation, so it would be positive. This force would tend to produce a clockwise rotation, so it would be negative. These 2 torques would cancel each other out, but the sum of the forces is not 0. So here's a case where the sum of the torques equals 0, but the sum of the forces is not equal to 0. So I just wanted to throw that out. Just because the sum of the forces is 0 doesn't mean the sum of the torques is also 0. And just because the sum of the torques is 0 doesn't mean the sum of the forces is also 0. And just while we're on here, if I'm looking at sort of Newton's laws, the sum of the forces equals ma. If I have a system where the sum of the forces is not 0, it will accelerate. And this A is really my translational acceleration of the center of mass. So if the sum of the forces is not 0, that means the center of mass of the object or system will accelerate. If the sum of the torques is not 0, then anytime the sum of the torques isn't 0, I'm going to have an angular acceleration. And so this is really a rotational acceleration. So going back, what's going to happen in this very first case? Well, the sum of the forces is 0 here, which means that the center of mass of this object is not going to accelerate. So it's going to stay where it was if it was initially at rest, but I am going to rotate about the axis. In case B, where the sum of the torques is 0, but the sum of the forces isn't, if the sum of the torques is 0, it means it's not going to rotate. There's not going to be any angular acceleration. But if the sum of the forces isn't 0, then the entire center of mass of the system can accelerate. Okay, what I want to do is really just 2 more example problems, and then we're kind of going to be finished with chapter 20.
Wait, so the answer to that clicker question was
So the answer,
C, right?
The answer was no.
Okay.
So if the sum of the forces is 0, it doesn't mean the sum of the torques has to be 0. And if the sum of the torques is 0, it doesn't mean the sum of the forces has to be 0. Okay, so what I want to do, just a little preview the last 2 example problems. One, what I want to talk a bit about at the end is if a pulley is not massless. We've seen this system before with 2 masses connected by a stretchless, massless rope connected over a massless, frictionless pulley. And remember, if the pulley was massless, the tension in each side of the rope was the same. Well, if a pulley is no longer massless and we start considering pulleys with mass, then the tension in each side of the rope is no longer going to be the same. So that'll be the last thing we're going to look at. And that's 20 minutes. That's fine. So what I want to do is just do one more sort of problem dealing with torque and angular acceleration. So this is problem 1228. A 4 kilogram, 36 centimeter diameter metal disc. So one metal disc, moment of inertia is 1/2 mr squared. You're going to use that for any solid disc, and any pulley we're pretty much going to model as a disc. So it can rotate along an axle along its center. A steady 5 Newton tangential force is applied to the edge of the disc. What is the disc's angular velocity in revolutions per minute 4 seconds later? A couple things about this. When you're dealing with angular quantities, everything you want to do in radians, and then at the end convert it into revolutions per minute or revolutions or something like that. So when you're using equations of constant angular acceleration, angles have to be in radians, angular velocity in radians per second, angular acceleration in radians per second squared. So we're given a force which is exerting a torque, causing this disc to accelerate angularly. And we want to know what is its velocity 4 seconds later. Okay, so let me see if I can draw this. I can tell the answer is no, but the situation is I've got some sort of disc which has its axis through its center, and a tangential force is being applied. So the force is tangent to the end of the disc. The radius of the disc is 18 centimeters, so 0.18 meters. We're told the force has a magnitude of 5 newtons. And again, if I ever want to know what is the angle that I'm going to use for the torque produced by a particular force, it's always the angle between the r vector, which points from the axis of rotation to where the force is applied, and the force vector. So the way I have this thing drawn, the angle between these two is 90 degrees. So first thing I'm going to do is figure out what is the angular acceleration, and then I'm going to use equations of constant angular acceleration to get how fast it's traveling. So Newton's second law in rotational form says the sum of the torques equals I alpha. There's only one force exerting a torque, so the sum of the torques is just going to be R times F times the sine of 90 degrees. Our moment of inertia is the moment of inertia of a disk, which is 1/2 mr squared. And let's just be consistent with these R's. Sometimes I use capital R, sometimes I use little r. Doesn't really matter. So this is R squared, and then, come on, times alpha. So I have R, which is 18 centimeters, 8.18 meters. I have F, which is 5 newtons. I've got the mass of the disk. I've got the radius of the disk. All I'm doing is solving this equation for alpha. Let me just skip that math part. What you'll find is that you solve for the angular acceleration, and what you're going to get is 13.9 radians per second squared. Again, this is pretty much like you're doing Newton's second law when we were doing it before. I use Newton's second law to get the acceleration, and then I can use equations of constant acceleration to figure out how far it traveled or how fast it's going after a certain amount of time. So for this, we use Newton's second law in rotational form to get the angular acceleration. So the sum of the torques, there was only one force acting. So the torque was just RF sine of theta, which was 90. I, for this case, it's a disk, so it's 1/2 mr squared, and I'm just solving this equation for alpha. Now I want to know how fast is it moving in revolutions per minute 4 seconds later. So our quantities are, we have omega naught, we have omega, we have alpha, and we have t. I could let theta naught be 0 and figure out how many revolutions it went through or how many radians it rotated through, but we just want to know how fast is it going. So it started off at rest. So my initial angular velocity is 0 radians per second. I want to know how fast is it moving after 4 seconds if the angular acceleration is 13.9 radians per second squared. Remember, for every equation of constant acceleration we have in dealing with linear quantities, we have the exact same equation. So instead of Vx equals V naught x plus AXT, we have omega equals omega naught plus alpha t. My omega naught was 0. So what I get is my angular velocity is going to be 13.9 radians per second squared times 4 seconds. What I would get is, what do I get? 55.6 radians per second. And I'm just going to skip this conversion. You can then convert from radians per second to revolutions per minute. 1 revolution is 2 pi radians, and obviously 1 minute is 60 seconds. What you would find is that this ends up being equivalent to 530 revolutions per minute. Booyah. Okay, what I want to do is ask one more clicker question and then just go on to this very last thing about pulleys that aren't massless, how they affect the tension. So very last clicker question is, a mass is hanging from the end of a horizontal bar, which pivots about an axis through its center, but it's being held stationary. The bar is released and begins to rotate. As the bar rotates from horizontal to vertical, the magnitude of the torque on the bar increases, decreases, or remains constant. So let's again do this as a quick little poll. So as this bar rotates from being horizontal to being vertical, what happens to the torque on the ball or on the bar? Does it increase, decrease, or remain constant? What do you think? Give you guys about 30 seconds to think about that. And while you are doing that, let me, why can't I do a couple things so we know torque equals R F sine theta. My F is just going to be mg. Okay, about 30 seconds. If anybody else wants to vote, what do you think? What do you think? All right, let's end this polling. See what people thought. Have about half people say that the magnitude of the torque decreases. Okay, let's see. So one, again, anytime I want to know the torque from a force, it's R, the magnitude of the distance away, times F, times the sine of the angle between them. In this case, what is the force? The force is just the force of gravity, mg, pulling down on this, what is it? This mass. Well, the distance away isn't changing, so R is a constant. The only thing that's changing is the angle. So like in this case, when it is horizontal, the angle I would use, my R vector would point to the left, my F is straight down. So the angle I would use would be 90 degrees when this thing is horizontal. Well, let's look not when it's vertical, but when it's right here. Now my R vector would be pointing in this direction because it points from the axis to where the force is applied. My force is still straight down. So now my angle is something less than 90 degrees. And let's look at it when this thing is hanging straight down. So now it's hanging down Here now my R vector would point straight down. My F vector would point straight down. The angle I would use would be 0 degrees, which kind of makes sense, right? If this thing is hanging straight down, there's going to be no tendency for this thing to rotate. There is no torque being applied to it. So what happens is, as this thing is hanging horizontal, I have the maximum torque. As it starts to swing, the angle between the force and the R vector starts to decrease. The overall torque decreases. And then when it's hanging exactly vertical, then the torque is 0. So the question is, if I let this system go, it's not just going to swing down and stop. What's going to happen is it's going to continue to rotate. Why? Well, I have an angular acceleration the whole time. It's speeding up until it gets to the bottom here. Now there's no more torque, but it's going to keep moving because of inertia. And then as it's swinging up the other way, the torque is going to tend to slow it down. So it's going to end up happening as this thing will start to oscillate back and forth. All right, let me stop that for a second. Check out what is the radians per second conversion to our revolutions per minute. I'm going to let you figure that one out. It's actually in the notes somewhere. And actually, just not to be coy, let's just find it. Clicker questions, lecture notes. I'm going to do that all the way up here somewhere. Boom, boom, boom. Revolutions per minute. Aha. So if I ever wanted to go from radians per second to revolutions per minute, so I know 1 radian per second, a revolution, 1 complete circle is really 2 pi radians. So I can multiply by 1 revolution over 2 pi radians. 60 seconds in a minute, multiply by 60 seconds over 1 minute. Seconds cancel out, radians cancel out. I'm left with revolutions per minute. And what you'll get is 1 radian per second is about equal to 9.5 revolutions per minute. Okay, so the very last thing is looking at pulleys that are not massless. So if you remember before, we were looking at this system many times in a couple different labs of an object on a massless or a frictionless inclined plane connected to another mass via a massless stretchless rope passing over a massless pulley. And the tension was the same. But key point, 1 second. Key point is this. 1, if the mass of the pulley is not 0, let me go to a different color. 2 things you're going to need to know. So if the mass of the pulley is not 0, 1, tensions are not the same. I can't assume that the tension on the part of the rope connecting mass 1 is the same as the tension on the part of the rope connecting mass 2. And just to be clear, if the tensions were the same, then one would be producing a positive torque, the other one would be producing a negative torque. Those torques would have the same magnitude. There would be no net torque, and so there would be no rotation. But if the pulleys is not massless, then the tension is no longer going to be the same. I have to have tension on one side being bigger than the tension on the other so that there's a net torque causing it to rotate. The other thing is, just like we relate the tangential speed to the angular speed by v equals r omega, what we're going to now relate is the angular acceleration of the pulley and the linear acceleration of the rope. And they're going to be related by the tangential acceleration of the rope, which will be the same as the tangential acceleration of the masses is going to be equal to r times the angular acceleration of the pulley. So this equation, a tangential acceleration equals r alpha. So this is going to relate the acceleration of the rope and masses, because they're all going to be the same, to the angular acceleration of the pulley. And this will be true. The one assumption we still need to make is that the rope doesn't slip on the pulley, meaning when the rope moves a certain distance, the pulley is going to rotate with the rope. I'm not going to have the rope sliding past the pulley. So if you remember when we did this problem way back when, and I'm going to recap it, but what we got was, well, let's just do it. Example problems.
Wait, can you go back for just a quick second?
To the lecture notes, this?
Yeah,
Okay. Is there a question on that?
I just didn't have time to write it down.
Okay. Oh, I have it here, but I'm going to derive this for you again. If we had a massless pulley, and M1 is the mass that's hanging off the end, and M2 is the mass that's on the frictionless plane, the acceleration was M1g over M1 plus M2. Now what we're going to see is what is the acceleration if I do have a pulley that has mass. And one thing to keep in mind, when you do solve for an equation where I'm taking into account the mass of the pulley, if I then set the mass of the pulley equal to 0, I have to come up with the original equation I had before when I was assuming the pulley was massless. So going back to this problem, keep in mind that one of the things about doing these problems is we had to be clear about defining our direction of acceleration to be positive and taking into account directions. So like M1 is going to accelerate to the right, M2 is going to accelerate straight down. The magnitudes of the accelerations will be exactly the same as long as the rope cannot stretch. If the rope can stretch, then it's possible that M2 could move a different distance than M1. But as long as the rope can't stretch, M1 moves a certain distance to the right, M2 has to move that exact same distance down in the same amount of time. And if you remember, what we did is we drew Freebody diagrams. So for M1, I really just have 3 forces. I've got the normal force acting straight up. I've got gravity M1g acting straight down. And I've got the tension. And right now, let me just write this as T1, acting to the right. If I look at the sum of the forces in the x direction equals M1a, what I get is tension 1 equals M1a. So this is one equation for the tension. If I look at M2, there's only 2 forces acting on M2. I've got gravity, M2g acting straight down, and I've got tension, I'll call this tension 2, acting straight up. But here was a key point. If the acceleration points down and I define up as positive, then I need to use negative a in my equation. But if you remember, I always like to define positive in the direction of the acceleration. So I'm going to define down as positive. So what I get if I look at the sum of the forces in the y direction equals MAY. Let's be clear, this is M2. What I get is M2G minus tension 2 equals M2A. Here's the second equation. Now, if these tensions are the same, because I'm assuming the pulley is massless, so if, what did they say here? So now they're saying, assuming the pulley, so if the mass of the pulley, I'm going to use MP. If the mass of the pulley is 0, then I know T1 is the same as T2, and let me just call it T, kind of what I was doing before. So this is, let's just call this equation 1, equation 2. So if the mass of the pulley is 0, then equation 1, I can just write as T equals M1A. Equation 2, I can just write as M2G minus tension equals M2A. And then I have 2 equations with 2 unknowns. I solve for these, and what you're going to get is the acceleration is M2G over M1 plus M2, where M2 is the mass that's hanging off the end. I think I used M1 in the previous example. So this is pretty much how we did it if the pulley is massless. So before I then take into account the mass of the pulley, let me just pause this, see if there's any questions on just this particular setup of the problem. Now we're going to assume the pulley's not massless, in which case the tensions are not the same. So any questions I can answer on that first part? Okay, so let us continue. So key point here is if, and let me go to red, let's do some blue. So if the mass of the pulley is not equal to 0, then tension 1 is not going to be the same as tension 2. So now what I have is 3 unknowns. When the mass of the pulley was 0, I only had 2 unknowns. I had the tension, which was the same for both, and I had the linear acceleration. Well, now if the mass of the pulley is not 0, then I actually have 3 unknowns. I don't know T1, I don't know T2, and I don't know the acceleration. 3 unknowns, I need 3 equations. Well, these equations up here still apply, right? Because I wrote them as T1 and T2. I didn't assume that the tensions were the same. So this right now, I have 2 equations, but I have 3 unknowns. I don't know tension 1, I don't know the acceleration, and I don't know tension 2. I need a third equation. Well, the third equation is we're going to look at the sum of the torques equals I alpha on the pulley. So one, how do you draw a free body diagram of a rotating object? And what you really do is you draw the object, you sort of indicate the axis of rotation, and then you draw the forces acting on the object at the location they are. So we had T2, and so in this case, tension 2 is acting straight down. Tension 1 is acting to the left. So this is the forces on the pulley. Each one of these forces is acting a distance of r away, where r is the radius of the pulley. And so our equation is the sum of the torques equals I alpha. Now here's one thing I want to caution you on, and I don't want to go into it in great detail, but just like it's beneficial to define positive in the direction of the linear acceleration, I would also define positive for angular quantities in the direction of the angular acceleration. So this entire system, as M2 is falling, the disk is going to rotate clockwise. So my recommendation is, if I have a system which is rotating clockwise, I would define positive in that direction. So now what I'm going to do is sort of change my convention. Usually things moving counterclockwise are positive, the angles, the angular velocity, and so on, and torques producing a counterclockwise rotation are considered positive. But since my entire system is accelerating in the opposite direction, I'm going to change my definition of positive, which now means that any torque that produces a clockwise rotation is now considered positive, and any torque that produces a counterclockwise rotation is considered negative. I could go into bigger reasons why, but for now, I think that's just the best way of handling these problems. So again, my torques then, T2 is now going to be producing a positive torque, T1 is now going to be producing a negative torque. So when I do the sum of the torques, it's going to be T2. Let's do RF sine theta. So it's going to be R2 times T2 times the sine of 90 degrees minus R1 times T1 times the sine of 90 degrees equals I alpha. And let me get to that part in a second. The radiuses, or the distances from the axis of rotation, are the same for each. So this is really just R2 times tension 2 minus R, I'm sorry, this is really just R, oops, T2 sign. So I have r times t2 minus r times t1, just because the sine of 90 is 0. Now, here's what you do with all of these sum of the torques equals I alpha problem. You replace I with whatever equation is appropriate for the object. In this case, we're treating any pulley like a disk. The moment of inertia of a disk is 1/2 mr squared. So this is mass of the pulley times r squared. And the angular acceleration is related to the linear acceleration by a equals r alpha. So I'm going to replace alpha with a over r. What I get is r times t2 minus t1 equals, this r cancels out one of these, so 1/2 the mass of the pulley times the acceleration times r. I can cancel out r from each side, and what I get is t2 minus t1 equals 1/2 times the mass of the pulley times the acceleration. Here is the third equation that I now have, so I can figure out 3 equations with 3 unknowns. So the first equation, T1 equals M1A. Let me just write that down here. So I've got first equation. Whoa. First equation was T1 equals M1A. Second equation was M2G minus T2 equals M2A. And now here's my third equation. What I'm going to do is just solve each equation for tension, plug it into the third one. So solving this equation for tension, I get T2 equals M2G minus M2A. Now I'm going to take this equation, plug it in for tension 2, take this equation, plug it in for tension 1. So what I get is M2G minus M2A minus tension 1, which is M1A, equals 1/2 the mass of the pulley times A. If I then gather all the terms that have acceleration on one side, what I get is M2G equals M1A plus M2A plus 1/2 the mass of the pulley times A. And then solving it for acceleration, what you get is, acceleration is M2G over M1 plus M2 plus 1/2 times the mass of the pulley. This is the final answer for if I have 2 objects connected together. One of them is on a horizontal frictionless surface, the other one's hanging down, but the mass of the pulley is not 0. Notice though, anytime I get an equation where I'm using the mass of the pulley because it's not 0, if I plug in the mass is 0, I have to get the original equation that I got way back when we were ignoring the mass of the pulley. So if I put in MP equals 0, what I get is my acceleration is M2G over M1 plus M2, which is just what we had before. Ha! Booyah! Okay. Let me see if I can access this chat. Isn't R the same? Do we need R? Yeah, so I was just being clear. The R's are the same, but I just wanted to be clear when we're doing torque, it's always the distance of that force from the axis of rotation. But yeah, these R2 and R1s are exactly the same. But just in case they're not, you always want to be clear about the values you're using. All right, so let me stop that. That is pretty much it for chapter 12. Couple things. So the homework for chapter 12 is due Thursday, quiz on Friday. The homeworks are more involved, obviously, than you're going to see on the, you got a speaker view. I don't know if that changes the way I record this. So the questions will be somewhat like the second celebration in the previous quizzes. They'll be fairly straightforward. It'll probably be 10 questions, multiple choice, maybe 5 of them conceptual, 5 of them being somewhat easy, straightforward problems. So as you're doing the homework, remember that the homework inputs may be different than the ones from the book. Solve everything algebraically and then put your answers in Mastering Physics. And also remember, the homework is still the homework I assigned at the beginning of the year. The solutions are all posted to sort of help you out. Could you go back to the notes for a second? Yes. Share screen. How do I keep chat open? There we go. Shinji, any questions particular about the notes here? Did you want to see something in particular? Yeah, not sure. So that, what is it, 12:10? Went about 10 minutes over. So we are officially done chapter 12. Just so you know, on Thursday, he wants what A is equal to. Perfect, thank you. You're welcome. On Thursday, I'm going to start chapter 15. Next week is our last week of classes, and I think I mentioned we have 3 more chapters to do, chapter 15, 16, and 17. Even when I normally cover these when we're live, I don't cover all of every chapter, but being online, I'm going to cover even less than I usually do. So I will be specific on lectures about what you can skip and what I'm covering, but pretty much no more PLCs, no more labs except for this lab that you're doing and then presenting next Wednesday. And then we'll have this quiz and homework on chapter 12, a quiz on chapter 15, 16, and 17, but we're the home stretch. I appreciate the fact that we've got almost 40, yeah, almost 2/3 of the class coming to these Zoom lectures, so thank you very much. So I am bringing out lecture, bringing in office hours. I'll be around for about 20 minutes. If you have any questions on anything from chapter 12, or if you have any questions about proposed lab ideas for lab 10, stick around for 20 minutes. Thank you everybody who joined me live. Have a wonderful day. And I will be in office hours tomorrow. Just so you know, there is no lab lecture, anything like that. You know, it's a design your own lab at home, but I'll be available for office hours with John at the normal times if you want to run any of your proposed lab ideas by me. Thank you, everybody. Goodbye, goodbye. Enjoy the day. But yep, got office hours for 20 minutes. So if you have a question, unmute yourself, send me a text, let me know what it is.
Hey, Joe, I had a question in regards to the lab.
Yeah, what's up, Steven?
Oh, sorry. So I was thinking of possibly utilizing my at-home gym equipment that I have to possibly calculate like the tension in the the rope, because we have like this weight set that where you can. I was figured, well, I have the mass already for the weights, and I was figured, is it possible that I can maybe utilize the lab to calculate like how much work it takes to pull so much weight from them, or possibly calculate the tension in the rope that it takes to pull the weights up?
You can, but I'm hoping for these labs that you have a theoretical value to compare something to. So, you know, like if you, I know, like, you know, got like a lat machine or something, and I set the bar to 20 pounds, I know exactly how much force it would take to pull this at a constant velocity. So you could figure out how much work, but then what are you going to compare it to? So it's got to be something more than just, okay, I exert this force over a distance of 1 meter. Here's the amount of work I do. You want to have some sort of theoretical value to compare it to.
Okay.
I was trying to think, could you like pull the bar down, let it go? You would know how much force is being exerted upwards. But yeah, I don't know how you would do something like that. And also the weights would come crashing down. I don't want to do that.
Yeah, so I was thinking of that. And
it's
then
the beginning of an idea, but you would need to flesh it out a bit more.
Okay. I also had thought of possibly utilizing maybe like impulse momentum from the previous chapter we just did, using like a golf ball or like a tennis ball, like dropping it from so much height. I don't know if that makes sense, like how much energy could be conserved or something.
I mean, you can do something like one of the write-ups was, if I drop a ball during the collision, I know there's going to be sound and heat generated. So if I drop a ball from like 2 meters up, I know how much gravitational potential energy it starts with. And then if it only bounces on the first bounce to 1.7 meters, I could calculate how much energy was lost. And then on the next bounce, I measure how high it is. And what you could look at is it losing the same amount of energy on every bounce? Is it losing the same percentage of energy on every bounce? Something like that. To do impulse momentum theorem, again, it would be hard to have a theoretical value to compare it to. So you could look at that collision trying to use impulse and momentum. I'm just not sure what kind of meaningful value you can get to try and compare something to it.
Yeah, that's what I was having trouble with, even with the weights thing. So I was like, I feel like I'm missing something, but I thought it would be a pretty cool idea since to utilize at home.
Yeah, I mean, one of the things about these labs is, one, they're challenging because it's hard to measure. You can't measure force in newtons unless you have a force sensor, which most of us don't. You can't measure mass in kilograms. And so a lot of this, you kind of have to make up your own units.
Okay.
And a lot of these, you have to really think about what is some sort of theoretical value that I can test.
Okay. That
But
makes
yeah,
sense.
I'm expecting people to have to try things a couple times, because when you're really making a lab up, there's all these little things that you don't really think about until you go and you set it up.
Yeah, exactly. Okay, well, I was just, I wanted to run that by you first before I got anything
Okay.
started.
Yeah, and if you have other ideas, I'll be around for a couple hours of office hours tomorrow.
Okay, thanks, Joe. I appreciate it.
All right, take care.
Joe, I got a question on the homework.
Okay.
It's number 7. It's a thin disc with the diameter, rotates about an axis through its center.
Here, hold on a second. Let me,
Yeah.
I think I can share this, share screen. Okay, problem 7.
Yeah, problem 12 or problem 9 maybe.
A thin 100-gram disc with a diameter of 8 centimeters rotates about an axis through its center with 15 joules of kinetic energy. What is the speed of the point on the rim? Okay.
So my thought process was, I was saying, okay, well, it's rolling, kinetic rolling. So I
So
said,
wait, here, be clear, it's not rolling. It's
Got
just
it.
rotating. So it's like a big merry-go-round that's just rotating on its axis. So the only form of kinetic energy is the 1/2 I omega squared.
got it. Okay.
So
That
you
answers-
so they gave you the total kinetic energy, so you could solve for omega. That'll tell you the rate at which the entire thing is rotating in radians per second, and then you can plug in R to get, so you know that, so you're basically doing 9. Kinetic energy of rotation, which equals 1/2 I omega squared. You can solve for omega because they gave you the kinetic energy. You can use the moment of inertia of a disk.
Okay.
But if I want the speed at a given point, that's when I'm using V equals R omega. So you're going to get omega by solving for the equation from before. And then you know the diameter, so you know what the radius is. So then you can figure out how fast the point on the rim is moving.
Perfect. Thank you.
You are welcome. Just got that.
Hey,
Marco, you got a question?
yeah. So I was working on like the block finding friction and stuff, and it turns out like you said, without a radar gun, it's pretty tough because like all the apps don't work. And then like I went to like check out some radar guns online, and like just because I got to return them like right after, and I guess you need to be on like 25 miles an hour, like at least to be like accurate.
Yeah.
Which sucks. So I'm gonna be using like this GPS app to like track my speed and stuff.
Okay.
And I'm gonna build like a giant ramp and stuff. And I was wondering if I could have like the initial final speed, and then I get time and stuff, and I have distance. Then how would I find the acceleration? Would I just
So remind me, I've had a bunch of people talk to me. Remind me the big setup of your lab.
I'm just gonna have like a giant ramp of like cardboard probably, and then I'm gonna just try and find the friction coefficient by like sliding another thing down, maybe cardboard or like foil, to find the friction coefficient between them.
All right, let me share screen for a second. So my thought, so you're going to, have something going down a ramp where it's starting from rest, and then you want to know like what is the acceleration when it gets to the bottom of the ramp?
Yeah, because then I'm going to use Newton's forces to find the friction coefficient.
So yeah, I would then use kinematics to figure out the acceleration. So
Okay.
if I define my x-axis as positive down the ramp, my y-axis is positive perpendicular, I know this is going to start off at rest. So v naught x is 0. I know I can let x naught be 0. X is going to be the distance it slides down the ramp. So distance down ramp. And what I'm looking for is acceleration in the x direction. So, the other thing I was going to say is what you could get then is t. So, I mean, every cell phone's got basically a timer on it. So if you measure how long it takes to travel a certain distance when released from rest, you can use equations of constant acceleration to figure out what the acceleration is.
Okay, yeah, sweet. That was sort of the plan.
So I think the easiest way is, don't try and do some sort of motion sensor or anything like that. Use kinematics. Measure the distance it's traveling, measure how long it takes to travel that distance if it starts from rest, and then you can just solve for the acceleration using kinematics.
Okay, sweet. Sounds good.
All right.
Thank you so much. Have a good one.
You're welcome. Any other questions? Leo?
Going back to the lab where you drop the ball and you calculate how much percentage of energy is lost to sound and heat.
Right.
If we were to try to find a theoretical value, how would we try to do that? Would we make a guess of how many bounces
No.
it takes?
So this is one where you don't really have a theoretical value to compare. But like the question John was proposing, which I kind of like, is, let me do this whiteboard again. Clear all drawings. So, let's say that I'm dropping a ball from some known height. So this is how high I release it from. But then, so I can tell you its gravitational potential energy would be mg y initial. But then after hitting it, it only bounces up to less of a height. And then it bounces again to less of a height. And then it bounces again and so on. So one of the questions could be, is it losing the same amount of energy in terms of the number of joules on each bounce? Is it losing the same fraction of its energy on each bounce, or neither? So, like maybe this started at, if I were to calculate mgy, let's just say that this ends up being 2 joules. But then when it bounces back, it's only at 1.8 joules. It lost 0.2 joules, but it started off with 2. So it lost 10% of its energy. And then if it bounced again, maybe this is 1.6 joules. So what you can compare is it losing the same amount of energy in terms of the number of joules, or is it losing the same fraction of its energy as a percentage of its initial energy?
Okay.
So like in this case, it's losing 0.2 joules and going from 2 to 1.8, 0.2 joules again. Is it losing 0.2 joules every time? Or is it losing 10% of its energy on every time? Something like that. So for that, you don't have a quantitative thing to compare it to, but you're looking at, is it losing the same fraction of its energy? Is it losing the same amount of its energy? Something like that. And then you could also look at different balls. So does a golf ball result in a different amount of energy loss than a rubber ball or something like that?
Okay.
So you'll have to get a little bit creative in sort of how you present it, how you're writing it up, because you don't necessarily have not necessarily, you don't have a theoretical value to compare it to.
Okay.
Or one other thought is, I haven't done this search, but you could look online. I'm sure somebody may have done this at some point and find a theory that you could test. So, maybe you do a Google search and you find somebody that says that every time a golf ball hits the ground, it loses 17% of its energy to sound and heat. So it's something that you could find and test, just as a possibility.
Okay. Sound
good?
Yeah. All right. Thank you.
You're welcome. Got 5 minutes. Any questions? Uriel?
Hey Joe, so back to the example earlier today where the angle of torque increased.
Where the thing was started off horizontal and was swinging?
Yeah.
Yes.
Just based off of that, we can't necessarily say that as the angle increases, like torque decreases. Is that for any situation? Would that be true for any situation?
So for this particular case, again, let me share the screen and do it clear. No, I wouldn't try and generalize this to other situations. So in this case, let's just take it when it's here. So I've got a mass hanging off the end. So I basically have mg.
Mhm.
And then this thing starts to swing. And now we're at this intermediate position. I still had the same force mg. And now it's all the way at the bottom. I still have the force mg. Well, the torque, so one, in all cases, the distance from the axis of rotation is r in
Mhm.
each case. That's not changing. And the magnitude of the force is just going to be whatever the weight of the hanging object is. So when I go to calculate the torque in each case, rf sine theta, it's going to basically be r times mg times the sine of the angle. So for this particular setup, the only thing that's changing is the angle. For this first part, remember, I always draw the forces together if I'm looking at the vectors together. So my r vector would point to the right, my force vector would point straight down, so the angle I would use would be 90 degrees. That's when you're going to have the maximum torque, because that's when sine of 90 is 1. And now for this one, let's just say the angle is 45 degrees. So now again, my r points from the axis to where the force is applied. So here's r. My force is still always going to be straight down for gravity. So this might be, let's say, a 45-degree angle, which the sine of 45 is less than the sine of 90, so there's less torque. And then when it's hanging straight down, now my r vector points down, my f vector points down, so the angle I would use would be 0 degrees, which produces no torque, which kind of makes sense, right? If I have something that's free to pivot and I hang a mass off the end, it's not going to cause it to rotate if it's already hanging straight down.
Right.
I'm going to have the maximum torque when it's like this, but as it's swinging, the torque is actually going from some maximum value to 0 when it's completely vertical.
Okay.
Does that make sense?
Yeah, no, that part made sense. Yeah.
So the other thing to think about would be like if I had a object which could pivot here, and I'm exerting a force at the same location every time. Well, if I change the angle of the force that I'm exerting, that's going to change the torque.
Okay.
So
Yeah.
the torque depends on 3 things: how far away the force is applied, how strong the force is, and the angle between the force and the position vector r. All right, let me clear that.
Okay.
Stop that share. Any other quick questions? You got 1 minute.
I think I'm all good. Cool. Thank you, Joe.
Awesome. Have a wonderful day, Uriel. And
Good luck.
yeah, take care.